This morning's presentation is actually two presentations. The first, about 90 minutes on biostatistics, a refresher, and the second on clinical study designs. And just kind of as a disclaimer, first, I don't have any conflicts relative to this presentation. Kind of as a disclaimer, for those who are present, that this is really a review of biostatistics. It's not meant to be an exhaustive discussion of all concepts, obviously, of biostatistics in the 90 minutes that we have. And for those who are here for recertification credit, the second disclaimer is that this is really designed primarily for those who are sitting for, or will hopefully be sitting for the prep course at some point, but obviously it will serve as a review for those here for recertification. I'll hopefully try to tell you what I think you need to know for the exam. Obviously don't have insights into what questions might look like, but try to give you some pearls in terms of what types of things that you're likely to see. So the outline for today's presentation is shown on the slide. You can see we'll talk about variables, descriptive and inferential statistics, hypothesis testing, statistical tests, and decision errors. And I think you'll see that at some points we'll kind of skip around and touch on some topics and maybe not exhaustively go through those topics. Before we start, I'd like to put in a plug for a book that's available in the ACCP bookstore. I have no conflicts. I'm not an author or an editor, but it's a really good book for those preparing for the exam. You'll see slides about it. There's a stack of them outside at the bookstore. It's called The Clinical Pharmacist's Guide to Biostatistics and Literature Evaluation. It has lots of cases, questions, I think that would be very good in guiding your preparation for the exam, and also serve as a review for those here for the recertification piece of the course. So statistics, I do apologize for the fact that you have to sit through 3 hours of stats and clinical study design, but I think this is probably the topic that most people who are taking this course are the most nervous about. And so we'll hopefully try to dispel some of that nervousness as best we can. Stats obviously are a way of collecting, classifying, summarizing, and analyzing data. Whether they're demystifying or not, I'm not sure. Sometimes they present more problems than they solve to some. It's a means of quantifying clinical and laboratory data in a meaningful way, and we'll give some examples of that. Why do pharmacists need to know statistics? Obviously, hopefully this group knows why, but more importantly, for those sitting for the exam, what do I think you need to know from the standpoint of tests for this exam? This is a summarization from an article in JAMA almost 6 years ago now that shows the most common types of statistics used in the biomedical literature. And so I think this serves as a pretty good guide for showing you what kinds of things that you need to know for this type of an examination. And we'll talk about most of these. Again, not in great depth, but we'll talk about most of these, and hopefully that will get you on your way towards preparation. 25% of the pharmacotherapy exam is focused on these types of concepts, in addition to some drug information, literature evaluation type questions as well. So it's obviously a reasonably large portion of the exam, and again, hopefully this review will be beneficial. So let's start with types of data, types of variables in data. We'll first start with discrete variables, and these are variables that can take only a limited number of values within a given range. And there's two that we most commonly, two that are listed here that we most commonly refer to. One is nominal. This would be a yes-no type of question. Or in the case of sex, male or female, mortality, either dead or alive, etc. Ordinal, on the other hand, has some ranked specific order. but there's no consistent level of magnitude between those ranks. And the most common one that I see in the literature anyways, and the types of literature that I read, is the New York Heart Association functional classification. So we classify patients with heart failure based on whether they have, one, no symptoms at rest, or whether they have, whether they have no symptoms all the way through 4, where they would have symptoms at rest. And the magnitude between 1 and 2 is not necessarily the same between 3 and 4, or between 1 and 2. Okay? Now, a common error in the literature is to use means and standard deviations to describe these types of data. Okay, so I would expect, or you might expect, this type of exam question in terms of evaluating a case, perhaps, that uses means and standard deviations to describe ordinal data. And we'll discuss this a little bit more later on. Continuous variables, on the other hand, are counting variables. Okay, these are variables that can take any value within a given range, and we commonly refer to 2 of these, either interval scaled or ratio scaled. So interval scaled data are data that are ranked in a specific order. They have a specific change in magnitude between 1 and 2 and 3 and 4 and 5, etc. But the 0 point is arbitrary. And the most common scale, the temperature scale, either degrees Fahrenheit or degrees Celsius, are both interval scale data. Ratio scaled, on the other hand, are the same as interval scale, but they have an absolute 0. So most biological measures, blood pressure, heart rate, on a temperature scale, degrees Kelvin obviously has an absolute 0. Transition into statistics, we're going to talk about descriptive statistics, which are statistics that are functions that describe a data set, and inferential statistics. We'll talk about descriptive first and then inferential second. So descriptive statistics can be broken up into 2 pieces. 1, how we visualize a data set, and 2, how we describe a data set with some parameters. So there's a variety of different visual methods for describing data, such as frequency distributions. We'll look at a histogram in a second, and then scatter plots, simple plots of a y versus x variables, are frequent ways to visualize data. So this is an example of a histogram which shows anti-factor 10A concentrations and the frequency of those concentrations shown on the y-axis, anti-factor 10A concentrations shown on the x-axis. And this histogram is just a means of showing, for a given data set, what's the frequency of, say, anti-factor 10A concentrations that are 0.5, and you can see in this data set it would be 14. So we can visualize whether or not we think this is normally distributed data set. And again, we'll come back to this a little bit later. From pictures now to numbers in terms of how we describe data. The first numerical method that we'll talk about is measures of central tendency. And there are 3 measures of central tendency. The 2 most commonly used in the biomedical literature are shown on this slide, the mean and the median. I think everyone is familiar with how to calculate the mean or the average in a data set. It's also probably the measure of central tendency that's most well understood, but most abused as well and used incorrectly for certain types of data sets. The mean should only be used for continuous and normally distributed data. It's very sensitive to outliers, and outliers tend to pull that average towards the tail where that outlier is located. Medians, on the other hand, if you line up your data set from 1 to 100,000, the middle value is the median. It's very easy to calculate. My 7th grader right now in his math class is calculating medians. It's the midpoint. Half the values are above and half the values are below the median. It can be used for either ordinal data or continuous data. And it's especially useful in those situations in which there's outliers or in which the population is skewed towards, or the sample is skewed towards one side of the tail. The mode, in contrast to the mean and the median, is the most common value in a distribution, and it can be used for nominal, so yes-no type of data, ordinal or continuous data, and it's particularly useful in those distributions that have more than one mode, or bimodal or trimodal distributions. It describes meaningful distributions that have a large range of values. So let's now transition from measures of central tendency to descriptors of data spread and variability. And the most common one, again, that we see in the literature is the standard deviation. Okay, remember that the standard deviation is a measure of the variability that exists about the mean. Okay, and it should only be applied to continuous data that are approximately normally distributed, or that the user of this test transforms the data to be. Okay, so if you have to remember, and you should, it really should only be applied to continuous data that are approximately normally distributed. The empirical rule, which hopefully you remember, or I've jogged your memory now so that you will remember it now, based on your introductory biostatistics course somewhere back in the day, 68% of values in a sample fall within the mean plus or minus one standard deviation of the mean. 95% of values fall within 2 standard deviations of that mean, and 99% of values fall within 3 standard deviations of that mean. This is, I think, a testable point, perhaps to have you evaluate a data set to make some conclusions about what the number of people that exist in a particular spread of the variability of that data set. A couple of other random concepts relative to standard deviation. One is the coefficient of variation, and you can see the calculation for that is the standard deviation divided by the mean times 100%. Gives you a relative marker of the mean as compared to the standard deviation. And then lastly, the variance is the standard deviation squared, which is another concept that I think is perhaps a testable concept. The range, in contrast to the standard deviation, is really, really easy to calculate. Standard deviation, you need a calculator, you need Excel, some statistical program. But the range, if you know the highest value and the lowest value and you can subtract, then you can calculate the range. It can be applied to both parametric and non-parametric data, which we'll discuss a little bit later. It's really easy to compute, as we've said, but the size of the range is obviously very sensitive to outliers. If you have a really big value and a really small value, you're going to have a huge range, and it's not going to tell the reader or tell you very much about the particular data set. Percentiles are related to range, and it tends to reduce the size of that description. So, for example, the 75th percentile, the 75% of the values are smaller than that specific percentile number. You know, anyone who's taken a standardized test, such as the pharmacotherapy exam, will figure out where their percentile is after they take the exam. Percentiles don't assume any population distribution. Does not have to be normal. Doesn't have to exist. Doesn't have to be any other distribution as well. The interquartile range is the 25th to 75th percentile. So it's the 50% middle values that exist in that sample. And it's very common to use in descriptions in which ordinal data are used or non-parametric data are used, and it will be used in combination with the median to describe a data set. So here's a common error, or a common means to help you separate when the mean and the standard deviation versus the median and the range is the most appropriate mean. So we did an evaluation a couple of years ago, we introduced a new biostatistics course to our students at Purdue, and we asked them some questions about that exam. Or excuse me, we asked them questions about that course. And you can see there's 3 years of data, 2006, 2007, 2008. And we asked a couple of questions. One is, the examination questions in this course were appropriate to the material that was covered. And we asked them, using a Likert scale, we asked them to say whether they strongly disagreed or whether they strongly agreed. And you can see that in the first year of the course, this is the mean and standard deviation. This is the median and the interquartile range. They didn't like us very much. They didn't think our exams were very fair. But we got better, okay, over time. You can see the second year we had a median of about 4, and it was similar in the third year of the course. So my question to you is, and if you get your audience response cards out, which of those two, when we presented these data, we actually showed both the mean and the standard deviation and the median and the interquartile range in the paper that we published. Which of those was more correct? Green or red? Okay, good. I see mainly reds. There's a couple greens scattered throughout, and then the majority of you really don't care at this point. You'd rather be somewhere else. My boss is in the room here, and so I have to be very nice. Oh, I finally see him in the back there. I figured he'd be in the back and not in the front. So I have to be a little bit kind. I don't want to do anything really bad. All right, so the most appropriate way to show these data is using the median and the interquartile range. Okay, because these are Likert scale type data. And the difference between 1 and 2 and 3 and 4 is not necessarily the same. So why do we show both? We actually showed both because a reviewer asked us to show both. Because the reviewer thought it was more understandable to the reader if we showed both. Well, it's not correct. And so the median and interquartile range would be the most appropriate in this situation. Now, if there's any statisticians in the room that are experts at dealing with Likert scales, they might argue with me and say, well, sometimes means and standard deviations are okay in this point. For the purposes of this exam, okay, if you get a question like that, like this, you should respond that the median is the most appropriate means of describing these data. Okay? Okay, so to summarize, measures of central tendency should be presented along with measures of variability. So mean should be presented with standard deviations. I just gave the answer away. What measures of central tendency should be presented with continuous interval scale data? Means. Okay, and with ordinal data, medians. You could make the argument for a mode as well. Okay, so means with continuous interval scale data, medians with ordinal data. What measures of spread and variability should be presented with means? We've discussed standard deviations, and with medians, ranges, interquartile ranges, something of that sort. Okay, I think these are really important concepts that would be good if you made a highlight in your on your slides related to this. So let's look at an example as to how we would go through a data set and make some conclusions about that data set. So these are data that lists 20 HDL concentrations that were measured as part of a clinical study. And you can see the HDL concentrations, and I've asked you to calculate the mean, the median, and the mode of the data set. Calculate the range, the standard deviation, and the standard error of the mean, which we haven't discussed yet, but we will in a couple seconds. And then to evaluate the visual presentation of the data. Now, ideally, I have these bullets backwards. Ideally, you'd show and evaluate the visual presentation of that data first, and then put some numerical values to it, but I didn't in this case. So I would do this first. But here's the mean, the median, and the mode. You can see that the mean and the median are approximately the same. Okay, one is 60.8 and one is 61, and that is important. And we'll talk about why that's important in a little bit. You can see the measures of spread The standard deviation is about 10, and the range is 41. And here's the interquartile range, 54 to 65. The standard error, the mean, remember, is always going to be smaller than the standard deviation, which sometimes causes it to be abused in terms of use in inappropriate situations. So let's evaluate the visual presentation of these data. So here's a histogram again of HDL concentrations on the x-axis and the frequency of those on the y-axis. So I'll ask the question, just more rhetorical than anything else, do we think these are normally distributed? Okay, do we think we could fit, or I guess I do that later, I apologize. We'll get to this later. We'll ask the question and show you whether or not we would conclude that these data are normally distributed. This is obviously a pretty small data set with a pretty small n, so it's a little more challenging to make definitive conclusions about whether these were normally distributed. But we'll go through this in a few moments. Okay, so we're going to move from descriptive statistics to inferential statistics. So in this case, and this makes up the body of statistical tests, really, in choosing appropriate statistical tests for a given situation. So we want to make, when we use inferential statistics, we want to try to make conclusions about a population from a sample of that population. Okay, and we can do this in a couple of different ways. One is by estimation, typically using confidence intervals, or by hypothesis testing, which we'll go through a little bit later. But first, before we do that, we need to talk about population distributions, because that's a piece of inferential statistics. There's two commonly used discrete population distributions, and we're not going to talk any more of these than just showing them on a slide so that you recognize the name. One is a binomial, and two is a Poisson distribution. It's the only French word that I know, so I won't talk about anything else. The most common population distribution is a normal distribution, and I think it's the thing that most of you see in the literature. Most common model for population distributions. And anyone who took freshman chemistry, Chemistry 101, knows that the grading in those types of courses is frequently done on a bell-shaped curve, okay, where a certain percentage of people get Fs, a certain percentage of people get As. The important landmarks for this distribution is that the population mean, okay, is equal to 0. This is a little bit of statistical lingo before we get into the practical side, and that mean is, the population mean is referred to as mu. The population standard deviation is equal to 1. And little x and little s represent the sample mean and the standard deviation. So if you're reading through Biostatistics text to get ready for the exam, or for those who are recertifying to review, you may see reference to these factors. Okay, so graphically, if we look at this, this is what a normal distribution looks like. So again, the mean is 0, and the standard deviation is 1. So 2 standard deviations would be 2, 3 standard deviations would be 3. Remember back to the rule that we discussed, the empirical rule. 67% of the data fall between plus or minus 1 standard deviation, 95% within 2 standard deviations, and then 99% within 3 standard deviations. Okay? So let's look at our data set again, the HDL concentrations data set. Do we think this is normally distributed? And I would say, in looking at this data, yeah, it's pretty close. So here's where the word that statisticians use all the time is approximately normally distributed. Okay, so by looking at this data set, I would make the conclusion that this is approximately normally distributed. We'll try to apply some practical points to it now to make it a little bit easier to understand. Okay, so how do we assess this? whether or not something's normally distributed. Well, we use frequency distributions and histograms like we just did. But I think the most practical and the easiest way in which to do this when you have a real data set is to compare the mean and the median. And if they're similar, okay, if they're similar, and in our case 61 versus 60.8, I would argue is similar, then I would conclude that these data are normally distributed, or approximately normally distributed. There's a formal test, and when I lecture to our PharmD students, I try to give them something that they understand. I refer to this as the vodka test, or they actually refer to it as the vodka test by this long name that I won't pronounce. There's a formal test that you can do to assess normality, and you could do that if you needed to, or in a research situation that might be reasonable. Sometimes, though, when you're presented with a paper and you're trying to evaluate whether the t-test that someone used was appropriate, you don't have access to all of their data. You're stuck with a mean and a standard deviation, and you're trying to make some decisions about whether that t-test was appropriate in that situation. So it is challenging sometimes to evaluate whether the test was correct based on that paper that you're reading. And sometimes you can make some conclusions about how large the standard deviation is compared to the mean. If it's a very large standard deviation, then that may give you some clues, perhaps, that these data weren't normally distributed. But it is challenging. Remember, based on the empirical rule again, that the mean and the standard deviation define a normal distribution. Okay? So these parameters, the mean and the standard deviation, are parameters, just like in a pharmacokinetic study. Clearance and volume are parameters that describe the pharmacokinetics of that drug. In this case, the mean and the standard deviation are parameters that describe that distribution. And that's why we call it parametric. Okay, so let's talk a little bit about estimation and sampling variability that exists as part of a normal distribution. The distribution of means approximates a normal distribution. Okay, and we estimate this in a data set by calculating the standard error of the mean. 95% of the sample means lie within plus or minus 2 standard errors of the mean of the population mean. Okay, and the distribution of these means from these random samples is normal regardless of the underlying population distribution. A little bit too much statistical jargon in this particular slide. So let's go on to talk about the standard error of the mean just a little bit. Standard error of the mean is the standard deviation divided by the square root of n. Okay, again, I think a testable concept for those who may be sitting for the exam. The standard error of the mean quantifies the uncertainty of the estimate of the mean, not the variability in a data set. Okay? So it quantifies uncertainty of the estimate of the mean, not in the variability of a data set. It's useful to know the standard deviation because the 95% confidence interval in a sample is equal to or approximately equal to the mean plus or minus 2 times the standard error of the mean. Unfortunately, the standard error of the mean is often used inappropriately. Perhaps deceptively. In some studies, we'll look at a figure in a second, perhaps just because the author wasn't sure what they should use, and so they chose to use the standard error of the mean because it's smaller, always smaller than the standard deviation. So here's our HDL example again, which shows HDL concentrations. The orange shows the mean plus or minus the standard deviation, whereas B, or the yellow bar, shows the mean plus or minus the standard error of the mean. So hopefully if you've been awake for the last 2 or 3 minutes, You will respond that the mean and the standard deviation, or the green response, is the most appropriate way to represent these data. But you can see, and I know sometimes I fall prey to this in a paper, it's like, well, this figure is going to look really, really bad if I use the mean and the standard deviation because my error bars take over the whole graph. Well, that doesn't make it right. So in this is actually an example that the standard deviation is not all that big, and so it may be not the best example. But you can see, obviously in this case, the standard deviation bars are much larger than the standard error of the mean bars, and it makes your data look a little bit nicer. Okay, but it's not appropriate in this situation. Confidence intervals, probably among the most confusing concepts for things that you see a lot of. So 95% confidence intervals are the most commonly reported confidence intervals. And what these mean is that in repeated samples or repeated studies, that 95% of all confidence intervals will include the true population value. So if you do 100 studies, 95% of the time, those confidence intervals will include the true population value. 95% confidence intervals are the confidence intervals most often reported because they correspond to a type 1 error rate of a p-value of less than 0.05, okay, or 5%, which is the p-value or the type 1 error rate most commonly used in the literature. I've shown you an example of this. You can go through this particular example. Just to remind you, though, that the standard deviation, the standard error of the mean, and confidence intervals are often used interchangeably, incorrectly, by typically people either writing papers or reviewing papers. You can use, instead of hypothesis testing, confidence intervals. And articles, and this isn't always the case, but articles that come out of the UK, such as Lancet, British Medical Journal, tend to use confidence intervals more commonly than perhaps papers published in the United States we tend to use standard hypothesis testing to draw our conclusions. But they really mean the same thing. Okay? Confidence intervals, on the other hand, help us to determine the importance of a finding by giving us some idea about this. I'm using the word spread. It's not the right word, but I can't remember what other word I want to use right now. But it gives us some idea of the spread of that population mean. Provides some magnitude of the difference. So in this case, if we're doing a test in which we are comparing, let's say, blood pressure between two drugs, and we're using confidence intervals, okay? A confidence interval that includes 0, okay, means that there's no difference between those two treatments, okay? So a confidence interval that includes 0 or no difference is not statistically significant. There's no need to show both the 95% confidence interval and the p-value. It's redundant. But many authors do in baseline characteristics tables or in the literature. We'll talk about confidence intervals for odds ratios and relative risks in the second presentation, and talk about how the interpretation of whether or not something is statistically significant is a little bit different in that situation. Okay, so now let's briefly just refresh your memory about hypothesis testing and its application in this situation. Again, this is just 3 slides about hypothesis testing before we move on to the next topic, just to remind you about some concepts. So remember that the null hypothesis, or the question that we're asking when we set up a trial, the null hypothesis, or H sub naught, is written in such a way that that we write it such that there's no difference between the comparator groups. So we say treatment A is equal to treatment B. The alternative hypothesis states that there is a difference. Treatment A is not equal to treatment B. And then the results of this hypothesis testing will indicate whether or not there's enough evidence to reject the null hypothesis. And if we reject it, the null hypothesis is rejected, then we conclude that there is a statistically significant difference. If the null hypothesis is not rejected, then we conclude that there's no statistically significant difference. Remember, we're not concluding, if we write it in such a way as this, we're not concluding that the treatments are equal. Okay? All right, so let's move on to statistical tests and choosing a statistical test, perhaps the piece of this discussion that makes everyone the most nervous when they sit for this exam. So choosing a test is dependent on a bunch of different factors that are shown on this slide. The type of data, whether it's nominal, ordinal, continuous, the distribution of that data, again, whether it's normally distributed or not, the study design, whether we're using a parallel or a crossover design, presence of confounding variables. We won't talk about that this presentation, but we will a little bit in the second presentation. One-tailed versus two-tailed tests. Again, we won't talk much about that because you will primarily see two-tailed statistical tests in the literature. There's a smattering of one-tailed tests that I've seen. And then lastly, parametric versus non-parametric tests. Parametric tests assume that the data being investigated have an underlying normal distribution. We've talked about this already. They assume that the data are continuous, and that they assume that the variances that are being compared, or the variances in the 2 or 3 groups, are approximately equal. Okay, so continuous normal distribution with variances that are approximately equal. The assumption that we can deviate from probably with the least amount of harm is that third assumption, that is the variances being approximately equal. Parametric tests are fairly robust. We'll talk about some corrections that can be employed or applied in cases in which the variances are not equal. Non-parametric tests don't assume these factors. So why just use a non-parametric test in every situation? Well, non-parametric tests aren't as powerful as parametric tests, okay, when a parametric test could be used. So if we should use a parametric test and we use a non-parametric test, then that test is not as powerful as its parametric counterpart would be. Okay, so that's why we're going to evaluate which one we should pick versus which one we shouldn't. Okay, let's start with the student's t-test, and I won't go through the history of why it's a capital S and the student. You've heard that in the stats course before. You won't have that on an exam. Well, what I will tell you is you have to be a little bit careful because there's actually 3 types of t-tests, and there's actually more than 3, but there's 3 common types of t-tests. And we're going to start with a one-sample test. Okay, and the example that I like to give is if we measure the LDL cholesterol of every person in this room, we want to know if it differs from the average in the United States. We would employ a one-sample test. We have one sample. We have each cholesterol concentration of the folks in this room, and we're going to compare that to the national average. Okay, one sample tests are underlie the concept that we used in terms of whether a normal value in a hospital lab. That's how normal values are determined based on this one sample test, just like LDL concentrations here as compared to a population mean. So this is the easiest, perhaps easiest of the t-tests. The second test, the second type of t-test is a two-sample, often referred to in one of 3 vernacular, a two-sample t-test, an independent samples t-test, or an unpaired t-test. They all mean the same thing. 2 sample, independent samples, or unpaired. So we're comparing the means of 2 independent samples. Okay, we line up all the men on this side of the room, we measure their cholesterol. We line up all the women on this side of the room, and we measure their cholesterol. And we compare the average cholesterol between those 2 groups. Okay, they're 2 independent samples. Now, it gets a little bit more complicated that if we determine the standard deviations of those 2 groups and we conclude that they're different. Okay, and there's a test that we can use, or we can just use what's called the rule of thumb. And basically, the rule of thumb suggests that if the ratio of the larger variance to the smaller variance is greater than 2, then we would conclude that those variances are different. Not the standard deviations, but the variances. Okay, so the rule of thumb is that the ratio of the larger variance to the smaller variance is greater than 2, then we would conclude that those variances are different. There's a formal test for this called the F test. You can imagine what our students call that. And this was a formal means to compare variances. The rule of thumb is actually a little bit more conservative than the formal test. Okay, so if the variances are different, no big deal. We just use the unequal variance t-test. Okay, it's basically just a correction for the difference in that variance. Okay, so if variances are different, we use the unequal variance t-test. Now, this unequal variance t-test only applies to a 2-sample t-test, not the other types of t-tests that we've already discussed or that we'll discuss in a second. Okay, lastly, the paired t-test. Okay, so in this case, we're going to line up everybody on this side of the room. We're going to measure their cholesterol. Then we're going to give them simvastatin. 6 weeks later, you guys are all going to come back to Reno. We're going to line you up on this side of the room. We're going to measure your cholesterol again. Okay, so we have now 2 samples from the same person. It's a paired sample. And we're going to measure the difference between those 2 samples. All right, so it's a paired sample. 2 samples from the same person. Same animal, same person, however you want to look at it. It's also sometimes referred to as a matched samples t-test or a related samples t-test, because obviously that pre and that post measurement is related and dependent on the other. All right, a common error with t-tests is that if instead of wanting to compare 2 groups, let's say we want to compare, we put everybody on this side of the room that's from the United States, everybody in the middle here from Canada, and everybody here on the right from Mexico, and we want to know if the means of those 3 groups differ. The incorrect way to do that is to compare the United States with Canada, the United States with Mexico, and Mexico with Canada. Okay, that would be employing 3 tests when all we really need to do is 1, which introduces the next topic, which is analysis of variance. Okay, so one way ANOVA, the easiest and the most commonly employed ANOVA, compares the means of 3 or more groups. Okay, so again, that example of U.S. versus Canada versus Mexico, that would be the way in which we would compare the averages or the means of those 3 groups. And so this would be an extension of a independent samples t-test. If we could get infinitely complicated. Let's say we want to know if We put all the males on this side, all the females on this side, and we break them up into 3 different countries. Okay, then this would be a 2-way ANOVA, where we have 3 groups, 3 countries, and 2 factors, male and female. Okay, and we could get 3-way, 4-way, what have you, and get infinitely complicated. Lastly, repeated measures ANOVA. This now is an extension of a paired t-test. So the example of cholesterol before, cholesterol at 6 weeks, now we can extend that cholesterol at 1 year. Okay, we want to know if that cholesterol changes over time. That would be an example of a repeated measures ANOVA. Post hoc tests are frequently used with analysis of variance in an effort to control our type 1 error rate, or our alpha error rate. Okay, and this gets over the problem that we discussed about multiple t-tests. So when we do an ANOVA, we get 1 p-value. And all we know is that 2 of the means that we've assessed are different. We don't know which ones. Okay, perhaps the Canadian and the Mexican cholesterol concentrations differ, but we do an ANOVA and we get an overall p-value for that whole ANOVA and the 3 groups that we assessed. If we want to figure out which differ, the most commonly employed technique, at least in the biomedical literature, is to use post hoc tests. And there are 4 of them that are shown. The Tukey honestly significant difference test is basically using a t-test within the structure of the ANOVA. There's also Bonferroni and Chaffee, which are a little bit more conservative. And then Newman-Cools, or the student Newman-Cools, is another test. So this is more that if you see these, that you'll recognize what they are. And the whole means for these is to maintain an appropriate alpha error rate, okay, or a type 1 error rate. Okay, so let's switch gears from parametric to non-parametric tests. So non-parametric tests are typically used tests for ordinal data or for continuous data in which the assumptions of a normal distribution are not appropriate. Data are heavily skewed in one direction, or what have you. So ordinal data or continuous data that do not meet the assumptions of a normal distribution. Okay, so let's first look at tests for independent samples. So this would be cousins, okay, cousins of a 2-sample t-test. The Wilcoxon rank sum and the Mann-Whitney U-test are the exact same tests, just with a different name, that compare 2 independent samples. Okay, 2 groups, 2 independent samples. So again, this is the cousin of the independent samples t-test, or the 2-sample t-test. In terms of ANOVA, again, where we want to compare 3 or more groups, the Kruskal-Wallis 1-way ANOVA by ranks compares 3 or more independent groups. And again, it's the cousin of the 1-way ANOVA. Anybody want to guess what kind of post hoc testing we might employ if we use this Kruskal-Wallis 1-way ANOVA by ranks? We would use the Wilcoxon rank sum test within the structure of our initial ANOVA, okay, if we found a difference. Okay. On the related side now, so this would be paired samples, paired t-test. Note that both of these tests include the word sign, because we're looking at differences that exist between a pre and a post, and what the difference between those is, the sign of the difference between those. So sign test, and most people in this situation get a little bit confused because this also includes Wilcoxon. Just like the Wilcoxon rank sum test, the Wilcoxon sign rank includes that same word. So if you can think of sign, that may help clue you into the fact that this is a paired comparison or a related samples comparison. Again, so it's the cousin to the paired t-test. And lastly, the Friedman ANOVA by ranks is the cousin to the repeated measures ANOVA. Lastly, related to non-parametric data, I just want to focus on the first two on this slide because it's probably the most commonly employed or commonly used. First, chi-squared, probably along with the t-test, maybe the most commonly used test that we see in the literature, mainly used for comparing baseline characteristics. Okay, so what this test is comparing is basically for simplicity, we're comparing the proportions of some measure between two groups, or the percentage of some measure between two groups. The percent of males in this group versus the percent of males in this group. The Fisher's exact test is a correction that's used along with the chi-square test when very small groups, specifically less than 5 observations, would be included in a chi-square cell. And there will be an example of this later on in the presentation. But basically, the Fisher's exact test, I think the only thing you have to remember, it's a correction for chi-square when there's a very small number of observations in a chi-square test. Okay, so let's go through some examples, and there are some audio response opportunities here. I won't call you out if you're not paying attention, but unless it's my boss, maybe I'll call him out. That's why he sat in the back. All right, so this is a study in which rosuvastatin and simvastatin were given to 25 individuals in each group. Baseline LDL concentrations were measured. Final LDL concentrations were measured. And you can see there that the p-values in this particular situation are shown as being greater than 0.05, which hopefully shouldn't be a surprise based on the means and the standard deviations that are shown in this table. But basically, here's a piece of the baseline characteristics from that particular study. So it shows the number of men and women, okay, in the rosuvastatin and the simvastatin group, the number of smokers in each group. So obviously, with that smokers, there'll be some corresponding number of non-smokers. Obviously, 10 and 15 here, and 13 and 12 here. And then lastly, the baseline LDL concentrations. This would be a mean and a standard deviation to compare between the two groups. So just as perhaps it's intuitive, obviously the first two would be proportions or percentages that we'd be comparing between these groups. 12 out of 25 versus 13 out of 25 versus the same percentage in that other group. Okay, so the questions that we're going to go through are which is the appropriate statistical test to determine baseline differences in sex distribution, LDL, cholesterol concentrations, and the percentages of smokers and non-smokers in the rosuvastatin and the simvastatin group. Okay, so here's hopefully these colors correspond to the right colors, but if they don't, I apologize. Green for A, red for B, blue for C, and yellow for D. So sex distribution. First, we want to know if the percent of men and women differ between the two groups. How many for A? Okay, just hold up whatever card you want to hold up. All right, I see mostly I see mostly reds. Okay, so this would be chi-squared. That would be the correct answer in this particular situation. What about LDL lipoprotein cholesterol concentrations? Go ahead, hold up your answer. There's a lot of people not playing. All right, so mainly D. All right, there's some overachievers, perhaps in the room, who either know something about statistics or want to make me look bad, or some combination of the two. In this particular situation, C, okay, is actually a correct answer. Because with two groups, an ANOVA test is effectively identical to a two-sample t-test. Okay? But if D is on an exam, if somebody asked you this, you'd have to get credit for both C and D. Okay? But hopefully on an exam, we wouldn't be silly enough to give you two potential correct answers. What about the Wilcoxon signed rank test? I saw a couple of greens out there. Okay? And maybe the argument is, well, this is, how do we know these are parametric data? Well, it's mean and standard deviation. It's pretty close. But would the Wilcoxon signed rank test be correct anyways? What's the non-parametric equivalent of a two-sample t-test? The Wilcoxon rank sum test, okay, or the Mann-Whitney U test. All right? So this Wilcoxon signed rank test is actually a paired comparison, which in this situation, it is not. Okay, so we're going to ask a couple of other questions, again, related to the same data set. On this slide now we have baseline cholesterol or LDL concentrations. We have final LDL concentrations. And we have the change in LDL concentrations. That's basically the delta between that baseline and that final LDL. So we want to ask the question, which of the following tests is appropriate for determining the effect of rosuvastatin on LDL cholesterol? So we're only focusing on the rosuvastatin group. Okay, and then the second question is, the primary endpoint was a 3-month change in LDL cholesterol. That means we want to compare rosuvastatin with simvastatin. Okay, so let's first ask the first question, which is, which statistical test would be most appropriate to compare the effect of rosuvastatin on LDL cholesterol? Okay, and this is a bit of a trick. All right, so how many for A? B? C? D? Okay, anybody want to fill in the blank? If you had to fill in the blank, what would you say? Anybody? I heard paired t-test. Okay, so if you had to fill in the blank, we want to know what's the effect of rosuvastatin only from baseline to 3 months. Okay, those are paired samples, right? Is there a paired non-parametric test here? A is a paired non-parametric test. All right, I'm not meant to be tricky. I'm just trying to get the concept across that this is a paired non-parametric test. If we wanted to use a paired parametric test, it would be a paired t-test. Okay, what about the second question? Primary endpoint. This is the 3-month change in LDL cholesterol between rosuvastatin and simvastatin. Okay? D is the correct answer. So it's a 2-sample test. We're comparing the change between the two groups. Again, so it's 2 samples. Okay, decision errors. Let's focus a little bit on type 1 errors and type 2 errors. remember that the probability of making a type 1 error is equal to the significance level, or the alpha value. Convention, the statistical gods, set this usually to be an alpha of 0.05. That means that 5% of the time, we conclude that there is a statistically significant difference when one does not actually exist. Now, obviously, this is a pretty dangerous error that we make if we conclude that a new therapy is more effective than an old therapy when it really isn't. Okay, so that's why this error rate is set lower than a type 2 error rate, which we'll talk about in a second. The calculated chance that we made a type 1 error in a study is called the p-value. Okay, so if we conclude that a statistically significant difference is found, then that value is going to be less than 0.05. That calculated p-value that we obtain from the actual study. Now, my stats professor during my fellowship always told us not to be piggish with our zeros. So if we did a test and we found we compared two groups and our p-value was 10 to the minus 23rd, she suggested to us that that was being piggish if we put that in a paper. And the reason for that is because a lower p-value doesn't suggest any more importance than a p-value that's close to 0.05. It only tells us that that comparison that we observed was less likely to have occurred by chance. Doesn't mean it's more important if your p-value is 0.000000005 versus if it's 0.04. Doesn't mean it's any more important. It just means that it's less likely to have occurred by chance. Type 2 error rates, on the other hand, convention sets the beta error to be between 0.1 or 0.2. There are some unique situations now in which sometimes type 2 error rates are set to be lower than that. But 0.2 is the typical convention. 0.1 is sometimes employed as well. But in this case, we're concluding that no difference exists when one truly does. That is, not rejecting the null hypothesis when it should be rejected. Power, of course, is related. Power is 1 minus beta. And it's our ability to detect differences between groups if one actually exists. And it's dependent on a number of factors, including what our predetermined alpha was, typically 0.05, how large our sample size is, the size of the difference between the outcomes that we're actually trying to assess, and the variability for which the data that are being measured is. Power is decreased by altering these factors, okay, or by employing poor study design, which is perhaps going to increase our variability, increase our error, what have you, or using incorrect statistical tests. So if we use a non-parametric test when we should use a parametric test, as we've already discussed. Let's talk a little bit about statistical power analysis. Basically, the same concepts that we talked about just a second ago with type 2 error rates apply here. The same concepts. Obviously, these should be determined in all studies a priori. And the typical necessary components of estimating appropriate sample size are shown. Obviously, an acceptable type 2 error rate. We have to know the difference in the outcomes that we're observing that we think is clinically significant. And we have to know what the variability exists in this measurement. And we also have to know what a type 1 error rate is. Now, it'd be very challenging to ask you to calculate this on an exam. Okay, I suppose if the formula was presented to you, you could be asked to calculate it, but I would suspect that that is unlikely. But I think the concepts that underlie this are something that are certainly fair game. Just a little bit about statistical significance versus clinical significance. And if you look through PSAP, or if you look through this book, there'll be a fair number of questions, and they're usually really hard questions. You might think they're tricky. They're not meant to be tricky. That question this statistical significance versus clinical significance concept. As we've already discussed, the size of the p-value is not related to the importance of the result. Statistical significance does not necessarily imply clinical significance. Contrasting to that, of course, is that if there's a lack of statistical significance, it doesn't mean that the results are not important. And this is usually a common problem with small sample sizes, where we make a type 2 error and we don't find a statistical significant finding, but yet perhaps the results are still important, which is what the last bullet on this slide talks about. Whenever we consider non-significant, non-statistically significant findings, we should consider sample size. Was it large enough? What our power estimates were, and what the variability was that we actually observed in a study. All right, we're going to switch gears now and go back to statistical tests. Again, a couple of common statistical tests, correlation and regression, and try to separate these two, talk about what the similarities are between correlation and regression, and talk about what the differences are between correlation and regression. Okay, first, correlation. Correlation examines the strength of the association between two variables. Are two variables related to one another? It does not necessarily assess whether one variable predicts another variable, just if they're related. Regression, on the other hand, takes it a step further and examines whether or not one variable predicts another variable. Okay, so correlation, strength of association between two variables. Regression examines the ability of one variable to predict another variable. And I'm talking about the simplest form of correlation and regression, which would be simple linear regression or very simple linear correlation. The parametric correlation is called Pearson's correlation. Parametric, Pearson's. Okay, again, measures the strength of relationship between two variables that must be normally distributed, must be ratio or interval scaled data, so it's continuous data, and must be linearly related. So normal distribution, ratio or interval scaled, and linear relationship between the two variables. It's often referred to as assessing the degree of association between two variables. And again, doesn't necessarily imply that one variable is dependent on the other. Typical techniques, sometimes in studies, I take the wrong approach to doing these correlations, which is, I have 40 variables, and you try to find if there's a relationship between any of the 40 variables. Hopefully we, before a study, figure out which variables we think are going to be related to one another, and those are the ones that we do correlations on. But sometimes it's, unfortunately, a shotgun approach to try to figure out if we have anything that's related to one another. The Pearson correlation coefficient, or little r, ranges from -1 to +1 and can take any value in between. So -1 would be a perfect negative linear relationship, 0, no relationship, and +1, a perfect positive linear relationship. Basically, what the hypothesis test is doing is determining whether the correlation coefficient is different from 0. And this test is highly influenced by sample size. That means if you have 100 samples in a correlation analysis, it's really hard not to find a statistical significant relationship between those two variables. So the larger the sample size, the easier it is to find a relationship. Your R value might be really small, 0.2, and you still have a statistically significant relationship. So evaluate with caution when we're looking at correlations between two variables in which we have a pretty large sample size. Spearman rank correlation is the non-parametric cousin to Spearman's, and this can be used when it's not a normal distribution or we don't have continuous data. So it can be used for ordinal data or non-normally distributed continuous data. This is just a picture of what we just discussed. All the way to the left here is a perfect positive correlation. Obviously, as y goes up, x goes up. One in the middle is a shotgun blast, where there's obviously no relationship between those two variables. And then the one on the right shows a perfect negative correlation, again, as with a R value of -1. Obviously, some pearls related to correlation. The closer the R is to 1, whether it's positive or negative, the more highly correlated those two variables are. There's no consistent interpretation of the value of R. What I mean by that is, if you're in a laboratory setting where you're investigating perhaps an animal study or an analytical technique, an R value of perhaps 0.5, 0.6, perhaps is not very meaningful at all. But in a clinical setting, an R value of 0.5 or 6 might be very important. So I can't tell you an R value of 0.5 is important, okay, or an R value of 0.3 is important. It depends on the situation and on the thing being studied. Try to pay more attention to the magnitude of the correlation, that is the value of R, than the p-value. Okay, if you have 100 people, your p-value is likely to be substantially lower than if you do a correlation with 10 people or 10 observations. And always, always, always view the relationship between two variables. If it's nonlinear, we shouldn't be using this type of correlation analysis. Okay, so we always want to look at a picture. Okay, back to regression. So regression analysis is a technique that's related to correlation. There are lots of different types. We're going to talk about simple linear regression, in which we have a continuous outcome or dependent variable, and a continuous independent or causative variable. And there's two purposes for regression. One is to develop a prediction model, and two is to assess the accuracy of that prediction model. Any aminoglycoside nomogram that's published in the literature is based on regression analysis. Okay? Development of a prediction model. And this is true for, obviously creatinine clearance estimation is based on some type of prediction model. Development of a prediction model and accuracy of that prediction model are the two important components of regression analysis. So let's focus on the prediction or development of the prediction model first. We want to make predictions of the dependent variable from the independent variable, and y equals mx plus b obviously is the easiest or the most commonly employed approach in this case, in which we have a dependent variable, we have a slope, an independent variable, and an intercept. And we'll look at a picture of this in a little bit. Now, the accuracy of that prediction model is obviously equally important. We basically are describing how well the independent variable predicts the dependent variable. So an R squared here of 0.8, okay, or the coefficient of determination, or the R squared value, note that's a small r. the range of values now between 0 and 1 because we've squared that R value, so it takes away the negative values. And R squared of 0.8 means that 80% of the variability in Y is explained by the variability in X. A common testable concept. Being able to distinguish between what R means and what R squared means. So R squared, 80% of the variability in Y is explained by the variability in X. This is just a picture to kind of show how that is related to one another based on diagrams, again, where the shared variability is shown by the overlap of these three circles. Okay, so anti-factor Xa concentrations shown here on the y-axis versus an enoxaparin dose in milligrams per kilogram. So again, we would expect, in a perfect world, that as an enoxaparin dose increases, anti-factor Xa concentrations increase. So let's look at the box that typically shows up in a study such as this. And there's a couple things that we should know. One is the slope and intercept are estimated from the regression procedure that happens. And this can be done in Excel. It can be done on a mathematical calculator. It can be done by hand if you have a lot of time. So you can see here the equation of the line. Okay, y equals mx plus b. So 0.227 is the slope, and 0.097 is the intercept. The required assumptions: normally distributed data. Okay, normally distributed data. This R squared interpretation, this is R squared of what? 0.31. So 31% of the variability in anti-factor Xa concentrations are explained by an enoxaparin dose. Not very good. Okay? Better than 20%, not as good as 40%. We could predict from this equation of the line what anti-factor Xa concentrations we achieve with an enoxaparin dose of 2 or with an enoxaparin dose of 3.75. We could also look at it on the screen. We go up from 2 and across, a little bit over 0.4. That would be for 2. So what does that p-value indicate that we see in a regression analysis? It tells us that the slope is different from 0. That's all it tells us. I think everybody could look at that picture and say, yeah, the slope looks different from 0, right? So that's all that p-value tells us, if that slope is different from 0. Very similar to a correlation analysis, which tells us whether or not that R value is different from 0. All right, survival analysis, which I think is the last discussion of this first session. Okay, survival analysis studies the time between entry in a study and some event. That event could be death, myocardial infarction, any assessment, any event that we would like to measure. And censoring makes survival methods unique to other types of statistical tests. And by censoring, this allows us to not be impacted by when subjects enter into a study or when they leave the study. Okay, so survival analysis allows us to take that into account, such that subjects don't have to enter the study at the exact same time. Instead, we have this randomization or run-in phase that may go over a year, or may go over 6 months, or may go over 5 years in large trials. So survival analysis allows the different entries into those particular studies to vary with time. The Kaplan-Meier method is probably the most commonly used method, one that you see in the literature most commonly. And basically, the Kaplan-Meier method uses survival times, okay, to estimate the proportion of people who would survive for a given length of time. Basically draws a picture, shows us the two survival curves in those two or more groups. To compare those survival curves, we would use a couple of different methods perhaps. One is a log rank test, which compares those survival distributions between the two or more groups that the Kaplan-Meier curve estimated. Lastly, the Cox proportional hazards model allows us to evaluate the impact of covariates, things that we think may influence survival times, on the survival in those two groups. And it also allows the calculation of a hazard ratio as well as a confidence interval. So again, this is an example of hemofilter survival, meaning how long a hemofilter obviously survived in a particular individual versus time. Okay, you can see that the heparin group is shown here by the dark black bars, and the bivalirudin group is shown by these hatched bars. And again, this is not meant to be, we're not meant to be talking about the clinical piece of whether this is important or not, but instead just the statistical evaluation. So this picture is the Kaplan-Meier curve. Okay, and then the log rank test, there's an estimate of the hazard ratio as well as the confidence interval. In this particular situation, as we'll talk about in the next 40 minutes, you can see that the p-value is exactly 0.05 because this confidence interval includes 1. So it looks like one of those therapies is more beneficial, right? Although right on the cusp of statistical significance. Cox proportional hazards modeling allows us to evaluate the importance or impact of covariates in a particular data set. And it allows us to investigate several variables at a time, and ultimately allows us to calculate a hazard ratio or a confidence interval in this situation. Okay, I finished about 7 minutes earlier or so in the first 90 minutes, so we're actually going to take we'll go 10 minute, we'll do our 10-minute break still. I'll be available for questions in the front, and then we'll come back in 10 minutes to start our clinical study designs piece of this. Thank you.